Lesson 2.5, Complex Zeros and the Fundamental Theorem of Algebra. We're not going to spend a lot of time on this lesson. Many of the ideas are going to be a review from Algebra 2, so we're just going to talk about a few theorems in this lesson and then go through one example. The first theorem we needed to discuss is the Fundamental Theorem of Algebra. It says a polynomial of degree n has n complex zeros. So if we look at the degree of a given polynomial, say it's 7th degree, 7 is our highest exponent, this theorem says there must be exactly 7 complex zeros. Okay, remember what complex is referring to, complex numbers. Complex numbers account for every possible number we can think of, whether they're real or imaginary. Okay, so the basic idea of this theorem is that the zeros could be real, they could be non-real, they could be repeated. We just know whatever our exponent is, if it's x to the 7th, there must be 7 complex zeros. Next theorem we are going to talk about is the complex conjugate zeros theorem. Basically it says if a plus bi is a zero of f of x, then a minus bi must also be a zero. Okay, a plus bi, that's referring to our complex numbers. A is the real part. Bi, that's our imaginary part. Complex or imaginary zeros must and will always occur in pairs of 2. So if you have one imaginary zero for a solution, there must also be a pair that corresponds with it. That pair is called the complex conjugate. So for example, if we knew 3 plus 2i was a complex solution of our function, then we would also have to know that 3 minus 2i would also have to be a 0. They always occur in pairs. The next theorem, or this is more of a definition, but it relates to the last theorem. It is for any polynomial with an odd degree, 1, 3, 5, 7, so on. Every polynomial function of odd degree with real coefficients has at least one real zero. So what this says, if we have an even degreed polynomial, there might not be a real zero. If it's an odd degree polynomial, there has to be at least one. Okay? And I want you to think about, why could that be true? Why must this definition hold true? And what you need to use is the complex conjugate zeros theorem that we just talked about. Okay? Go back and look at what that theorem says and try to understand why this definition must hold true. Okay? That's something you need to investigate, and then come talk to me about it once you get done with this video. In this example, we're going to find a polynomial from given zeros. So if we know what the zeros are, we're going to write the polynomial function that has those zeros in the lowest possible degree that we can. This is going to be similar to examples 2 and 3 in your textbook. I would suggest looking through those examples as well, just so you have a better understanding. So suppose that we have 5 and 3 plus 2i. We know these are the two zeros for our polynomial function. And we're going to try to write an equation that has these zeros. Before we can get started, let's just look at our zeros, try to understand what we have. We have 5. 5 is a real number. Okay, that one's pretty easy to work with. 3 plus 2i. Real part, imaginary part, that's a complex number. From our complex conjugate zeros theorem, if this is a complex zero, remember they occur in pairs, so 3 minus 2i must also be a 0. So they don't tell us that in the problem. That's something we have to conclude because of our understanding of complex zeros. They must always occur in conjugate pairs. So if x equals 5 is one of our zeros, we can write this in factored form as x minus 5. If 3 plus 2y is one of our zeros, we can write this as x minus 3 plus 2y. And similar idea for 3 minus 2y. That's going to be the same as x minus 3 minus 2y. Okay. I just use brackets because we should use parentheses around our conjugate pair zeros, okay, just to keep everything a little more organized. Now what we're going to do is multiply all of these terms out. And the thing you should do is multiply these two out first, your conjugate pairs. Because if you multiply those out first, you're going to get some things that cancel, make it a little easier to work with. So, x minus 5. And before we do that, I'm going to simplify this. I'm going to distribute this negative to each of those terms. Okay? So distribute that negative, distribute this negative to each term. So this is going to become x minus 3 minus 2i. And this is going to become x minus 3 plus 2y. So if you multiply those last two factors together, yes, you get many terms. You get 9 terms actually, but a few of them will cancel out. We have a negative 6i and a positive 6i, so those cancel out. We have plus 2ix minus 2ix, those cancel out. So now if we look at what we're left with, x minus 5 times, we have an x squared, and that's the only one, minus 3x, combine those terms, negative 6x. So we got rid of those, and then we have 9, and then we have a negative 4i squared. Remember, this is the same as negative 4 times negative 1. I squared is a value of negative 1, so that's actually just positive 4. So 9 plus 4, we get plus 13 at the end. Okay, so now you should go through and multiply these two polynomials together. Okay, so if you multiply those last two factors together, x minus 5 times x squared minus 6x plus 13, you should get x cubed minus 6x squared plus 13x minus 5x squared plus 30x minus 65. Now we're just going to simplify this, and this will give us our polynomial f of x with its lowest degree that has those given factors. So we have an x cubed, gets rid of that term. We have negative 6x squared minus 5x squared, negative 11x squared. Then 13x plus 30x is 43x minus 65 at the end. So f of x equals x cubed minus 11x squared plus 43x minus 65. This is a polynomial function that if we would graph, we would see our real zero at 5, and it would also have two imaginary zeros. Okay, those two that we started with, 3 plus 2i and 3 minus 2i. Alright, so now you're going to have a couple of problems to work on. Those problems are going to be on page 215. And the only ones we're going to do are 5 through 7. Okay, so this is something you need to get done right away. This isn't a regular homework assignment. It's more like a checkpoint. I just want to make sure you can understand how to write these polynomial functions from the given zeros.